This is a fantastic turnout for the first Core Connections lecture, and we're doing it a little bit different this year, and so I wanted to tell you guys how it's working. The first two lectures are the lectures for the fall semester are going to both be around the first theme of the core curriculum that all of you guys are involved in. They're going to be about environmental awareness. The ones in the spring are going to be about social global awareness. So we're trying now to be a little bit more thoughtful so that you can see how these things fit in with your core curriculum. Our first speaker is Dr. Brad Singer, and he is from the University of Wisconsin-Madison. He's in the Geosciences department, and he's the chair of the Geosciences department. And as are a lot of academics, he is bounced around all over the place. He's originally from Southern California. He got his bachelor's degree at UC Santa Barbara. Yes. He got his master's degree at the University of New Mexico. Any applause for that? Thank you. Then he got his Ph.D. at the University of Wyoming, and then he decided that he was going to take a little trip around the world. And he went to the University of Michigan. He went to Southern Methodist University. He went to a university in Switzerland before he finally landed at the University of Wisconsin, where he has been for the last 14 years. He is a very accomplished geologist. He has over 130 different publications on geology, and today he's going to talk to us about, is the next super-eruption brewing in the Andes? So again, the whole theme for this year is disaster. So we're starting with a very large one, the super-eruptions.
Thank you, Charles. I want to thank Charles and Eric for inviting me to participate in this lecture series. Had a great visit so far. And I understand that not all of you are science majors. You have different levels of exposure to the earth sciences. Many of you who are science majors are in the marine sciences, so I'll try to go a little bit slow here and through some of the basics and what drives these kinds of systems. And the star of the show here is in the first slide. This is the Laguna del Male volcanic field on the top of the Andean range crest. This is about 400 kilometers south of Santiago, the capital of Chile. These results, some of the ideas and data I'm going to show you today come from a large project that I'm the leader of. We have about 30 different scientists, including several Ph.D. students and postdocs at several universities, including my own university, but also in Chile. We're working very closely with the Chilean government. This is the National Volcano Hazards Group and the National Volcano Observatory, who's working with us. So it does say, looks like it small mention of a volcano, and we can pack the room here. It's a pretty exciting topic, and I'm really glad to see this many people out here for this subject. So here's our topic, and what I'll do here in this talk is review rhyolitic super-eruptions in their global context very broadly. We'll talk about what a rhyolite is and what the definition of a super-eruption is, so you can get an idea of the scale of these phenomena and what goes on. And what I would like to share with you is how geologists and geophysicists traditionally look at these systems. We end up having to be forensic scientists. We end up looking at the aftermath of these kinds of processes and doing the best we can to reconstruct what happens from the leftover deposits and calderas that impact the Earth's crust and are left behind. And that's taken us to a very high level of understanding of these systems, but we're entering a new era where technology and the kinds of approaches that we're able to take could allow a pivot point and allow us to start looking at systems that are actively in the process of growing to the point where they may produce super eruptions. And I want to stress this and some of the tools that we use as geoscientists in investigating active systems for the latter half of the talk. We'll talk about satellite geodesy, geologic ground truth, geochronology, which is my specialty, dating the ages of eruptive products from these kind of volcanic systems, and we'll talk briefly about the kind of computational simulations that we would like to do were we to be supported by our National Science Foundation at the level we think this project eventually deserves. Laguna del Maule is a natural laboratory that'll be, again, the star of the show here. Now, here's a couple of different volcanoes that express eruptive behavior very differently. One is Arenal in Costa Rica. This is a fire fountain that tourists can go see there any day of the week at this volcano. And you see this much different kind of behavior at Mount Unsen. This is 1991, the 1991 dome collapse at Mount Unsen. And Earth scientists and you should all be asking yourself, why the difference in explosivity? This is a relatively passive event with fire fountaining and bombs falling on the slopes, incandescent bombs of lava falling on the slopes of the volcano, coalescing and flowing away as lava flows. Very fluid behavior. And the main reason is the composition of the magmas are different. This volcano is predominantly basaltic, and what that means is the magma has a low number of silica atoms for every oxygen atom in the magma. And these are typically very high temperature, and the fact that there are a limited number of silica atoms to bond with oxygen to form this important molecule here means the magma has very low viscosity. It flows almost like water at these kind of temperatures. It also has low ability then to trap and hold on to water molecules that might be dissolved in this magma as it's ascending through the Earth's crust, okay? And this leads to weak explosivity. All the water diffuses out of the magma before it gets to the surface, and there's nothing to promote eruption. The contrast to that are these dacitic and rhyolitic volcanoes like Mount Unsen in Japan. These have a very large number of silicon atoms in the magma relative to oxygen in this molecule. These are low temperature materials, and because of the ratio of the silicon to the oxygen in these magmas is so high, these are very stiff materials. These are more like toothpaste. They're very rigid as magmas, and they can hold on to all the water that the magma is carrying towards the Earth's surface. Well, at some point during that ascent path, the water cannot stay dissolved in the melt. The pressure becomes low enough that the water bubbles start to form in the melt. And as anybody who knows who's opened a soda can after you've shaken it or agitated it, if you open a soda can, it'll explode on you. That's exactly what's happening here, is we're unroofing the top of the magma body somehow and allowing the magma to decompress a little bit, to lose pressure, and it loses the ability to hold all this stored water, and the water literally expands, the bubbles expand, fragment the magma, and blow it apart. That's what leads to these explosive eruptions. So the main issue here is the composition. So what I'm going to be talking about are rhyolitic eruptions, like the one here at Unsen, but on a scale that's a little bit different than what we see at Unsen. So before I do this, let's show you a video of what an eruption like the one at Unsen produces. Can we get that running here? So this video was taken by David Lay. The narrator is a very famous volcanologist from Great Britain, Steve Sparks of Bristol University. I'm going to run this for about 2 minutes. This just shows you what a modest silica-rich explosive eruption does at a volcano like Unsen. So you can go ahead. And there'll be some sound with this, I hope. You're going to have to put the, yeah, there we go. Go. If we could go get that for the whole screen with sound, that'd be great. So the audio's not playing. We need the sound here. I could try to narrate this. I might do it injustice here. Montserrat, Soufriere volcano in Montserrat in the Caribbean it's a small island. This is a relatively small andesitic volcano. Andesite is on the side of the Unsen type behavior that I showed you. less the basaltic type behavior. What you're seeing here is in 1996, there was a modest size eruption from the top of the Soufriere Hill volcano. And what you're seeing is the magma has decompressed and the water bubbles in it have expanded, and it fragments the magma and blows the magma apart. So at ballistic velocities, particles of ash, small fine particles of sand-size glass fragments, the melt, are being blown through the atmosphere, along with blocks the size of this room. Okay, and these start to flow down the sides of the volcano at first velocities on the order of several tens to hundreds of meters per second. This slows down and diminishes as you lose kinetic energy, as the gravitationally fed flow spreads out down valleys away from the center of the activity. It's too bad we don't have the audio for this, but this eruption here is a fraction of a cubic kilometer of magma being released to the surface of the volcano and producing these pyroclastic flows that are descending the slopes of the volcano. All right, and these eruptions began in 1995 and devastated this island. They pretty much wiped the population off the island. Nobody lives here anymore. Okay, for those of you who can stick around afterwards, we'll get this running again with the audio, but we can go back to the PowerPoint slide. This is called co-eruptive ash. This is the flow. This is 700 degree, 800 degree material moving down the valleys here away from the vent. There's enough air being incorporated into the flow that the ash becomes buoyant, and is actually producing a big column of ash that gets strewn out by the wind in the upper atmosphere and can get carried a long way. Okay, we can turn this, let's turn this off and go back to the PowerPoint, please. And so we get that up on the full screen. That eruption that you just saw was a fraction of the size of the one that took place 30 years ago at Mount St. Helens. This is a scale of meters of lava, or cubic meters of kilometers of magma erupted. And these are some examples of the dozen or so eruptions that have happened in the last few hundred years that are common around the planet. And these range from on the order of a cubic kilometer to a few tens of cubic kilometers. So again, you might be familiar with the eruption of Pinatubo in 1991 in the Philippines that caused the closure of Clark Air Base and the evacuation of some several hundred thousand Filipino citizens who lived on the slopes of the volcano. That was a modest size of eruption of about 5 cubic kilometers. And there are these others. The biggest historic eruption by far was this eruption of Tambora in 1815. This killed several tens of thousands of people in Indonesia. This is what humans have some experience with. If we go and look at the geologic record, here are those recent eruptions on a slightly different scale here. Cubic kilometers of magma erupted during one of these events. And these are the volcanoes, including this one at Montserrat that we were just looking at. There are a class of volcanoes that erupt several hundreds to several thousands of cubic kilometers of silica-rich magma. Those would be in this class over here. Anything above here is called a supervolcano. That's just a term that some of my volcanologist colleagues like. I kind of detest it, actually. It's a little bit sensational here. There's evidence in the geologic record for hundreds of events like this having taken place on Earth. And the most recent one of these, the problems with studying these kind of systems, the most recent one took place in North Island of New Zealand about 26,000 years ago. So humans were not writing anything down here. We don't have a record of this other than forensically looking at the deposits that were left behind in the landscape. The best studied of these supervolcanic eruptions that are hundreds to thousands of times the size of what you just saw at Montserrat. The best studied is about 767,000 years old. It occurs in eastern California. I'll give you a quick tour through that deposit. That's called the Bishop Tuff. That's a 650 cubic kilometer ash flow tuff. That's the name that we give to the rock that's deposited from all that ash and blocks and gas that solidifies in the landscape and cools off. That's called an ash flow tuff, okay? This is an exceptionally well-studied example, all right? These kinds of eruptions at this scale are thought to have serious impacts on the climate at the global scale for on the order of decades. These inject huge amounts of sulfate and fluorine and chlorine into the atmosphere. We know this took place at Pinatubo, for example, and the atmosphere was cooled off a degree or two for about 5 years after the small Pinatubo eruption. Well, one can only imagine what would happen to climate in a hemisphere scale if we had an eruption of 2,500 cubic kilometers, or the Fish Canyon tuff here, which is well documented to be at least 5,000 cubic kilometers of rhyolite being erupted. These would cause serious problems for climate worldwide, and the ash would remain in the atmosphere and disrupt air traffic and so forth for probably years to decades. Not to mention the impacts on agriculture, which are well known in South America, where I'm going to be talking here. Even small eruptions from the Andes cause havoc in northern Patagonia and the Pampas in Argentina. The ashfall destroys the crops and the grazing conditions for livestock. So let's talk about some of these forensic investigations that people have done. We'll talk about looking at these ash flow tuffs and the pyroclastic flows. I'll just give you a little bit of a snippet of what kinds of things we learn from these kind of deposits. We'll talk about some of the geophysical methods we use to explore these ancient volcanoes that are left behind after these super eruptions. And we actually have this interesting way to study these things by looking at what are called granitic plutons. And you're actually fortunate you were standing on a granitic pluton below us here. It happens to be Ordovician in age, I think. It's several 100 million years old. But granite plutons are frozen bodies of magma. If this rhyolite doesn't erupt at the surface and create a super eruption, what happens is most of that magma freezes kilometers below the surface of the Earth into granite plutons. People have poured over these things in 3 dimensions where they're exposed by uplift and glaciation, and we get a good idea of what kind of processes were going on in these magma bodies by looking at granitic plutons. These are basically fossilized magma reservoirs for these kinds of systems. So let's take a look at the Long Valley caldera. Here's the edge of the caldera in eastern California, here almost on the border with Nevada. Here you can see the rim of the caldera here. The caldera is about 35 kilometers east to west and about 20 kilometers, 15 kilometers north to south. This is an enormous depression in the Earth's crust from which this eruption took place of ash and pyroclastic material, just like I showed you from Montserrat, that blanketed the landscape in this huge orange sheet. This is called an ash flow tuff. There's a person for scale right there. All right. Ash from this eruption that took place 767,000 years ago blanketed this portion of the United States of America in several centimeters of ash. So there's well-known ashfall deposits from the Bishop Tuff in Omaha, Nebraska. Okay, to give you an idea of the scale of this thing. What do we do with these kind of deposits? Here's a geologist for scale on that same outcrop, basically, and I'm not going to bore you with the details. I know you're not all geologists or scientists, but this is a plot of the concentration of a trace element called cesium versus the concentration of a trace element called tantalum. Okay, and what people will do is measure the compositions of these ash particles and pumice lumps, these golf ball to baseball or larger size clots of the inflated magma that get caught up in these deposits, and we'll just look at what are their compositions. What do the minerals tell us about the physical chemical conditions that the magma was seeing before the eruption? And so on this plot here, we've looked at the composition of oxide minerals that are in these pieces of ash and pumice, and that can give us an idea what the temperature of the material was before it was erupted. Okay, and the point of this is that I think you can see from these diagrams is that the bottom of this deposit has much different chemical composition than the top, And the material was stored below the surface of the Earth before the eruption at a much different temperature. In fact, the bottom of the deposit was stored at much lower temperature and has much higher concentrations of these trace elements than parts of the deposit which are up here. And so what geologists and volcanologists have done is you got to think about this as an inverted record of what the magma body was like. It was emptied out such that the top of the magma body came out into the landscape first. This was the top of the magma reservoir, and that has these characteristics. And the bottom of the reservoir, as you might imagine, was much hotter, and it had different chemical composition. And by looking at these gradients in composition, we can start to get a handle on physically and chemically what was going on inside this body. The other kinds of studies that are done more and more are looking at geophysical images of the calderas, like the Long Valley caldera that's left behind in the landscape after one of these eruptions. This happens to be the Yellowstone caldera. How many of you have been to the Yellowstone National Park? A good fraction of you have driven across this caldera, which is about 35, it's about the same size as Long Valley, 35 or 40 kilometers. It's an oval-shaped thing in diameter, and the big Lake Yellowstone is right in the middle of this thing. This last erupted about 650,000 years ago. So that eruption left behind an enormous crater. It wasn't the first of these kinds of eruptions from Yellowstone. And if you look at the way seismic wave energy passes through the crust, and this is done by placing seismometers out all over the top of this system and letting them record earthquakes and explosions and any kind of event that creates seismic wave energy that passes through the rocks, you can actually track the speed at which those waves pass through the solid rock here. So this is a cross-section cut through Yellowstone down to a depth of about 16 kilometers, about halfway through the crust. And what you can see is this tells you how fast the seismic wave energy was moving. And there are regions where it was moving pretty slowly, here in the brighter colors, and then there's this region of fast travel time. This is more solid and cooler rock, and these are interpreted to be pockets of fluid or melt that dampen out the ability of the seismic wave energy to travel through the rocks. It basically slows the speed of the seismic wave energy as it moves through the rock. And so we can detect whether or not there's large amounts of fluid beneath this system by looking at the seismic behavior. This is called seismic tomography. It's like a CAT scan, only using seismic wave energy. And in fact, below Yellowstone and below any of these supervolcanic calderas that have been studied, there's not evidence for very large, enormous volumes of melt being stored. There might be pockets here and there, but we might not expect to find a large batch of magma still there because most of it erupted onto the landscape and created the tufts of the Yellowstone Plateau. Here is a different way to look at these kinds of magma reservoirs, these supervolcanic magma reservoirs. That would be looking at plutonic rocks. And these are some examples that I'm starting to study with a couple of my graduate students in Madison. These are plutons that are very close, only 20 kilometers away from the volcanic system that I'll spend the latter half of the talk focused on. These two plutons that we're studying down here, this is one of them, are only about 6 million years old. We've dated them using radioisotopic methods that I can talk to you about after the lecture's over if you're interested. These have been exposed by uplift and deep erosion of the Andes over the last 6 million years, such that there's at least 1 kilometer of vertical relief. Here's the top of this pluton. You can actually see that it's much different rock than the surrounding rocks into which it was intruded. So this was molten magma of the same composition, this granite magma that was intruded into the crustal rocks. This is a frozen reservoir of this rhyolitic, silica-rich, potentially explosive magma. If we go in closer and crawl into this canyon, which is farther away than it looks, it's about 10 kilometers from where I took this picture, and it's pretty steep. Get up here and crawl into that canyon and start looking at it. You can really see the sharp boundary between the granite, which is a frozen coarse-grained rhyolite, and the wall rocks that the granite intruded into. It's very, very sharp contact. And this is about 1 kilometer, 2 kilometers across. That's about 2 kilometers here, and that's 1 kilometer of relief. So we can actually look around inside these bodies and start to reconstruct what these reservoirs might have been like immediately prior to super-eruption. This is another way that these deposits are studied. And ultimately, we come to pictures that look like this. This is based mainly on work on the Bishop Tuff in eastern California, the Long Valley caldera that we were talking about earlier. This is a very enormous body of magma that erupted the 650 cubic kilometers of Bishop Tuff. We imagine that was mobile, molten, liquid, high silica, rhyolitic melt with very low proportions of crystals sitting on top of a much larger residue of crystals that had formed as this magma body cooled in the crust. And in fact, if you just do some simple arithmetic here and look at the compositions I was talking about earlier, you have to put a lot of basalt in from the mantle, a lot of this low viscosity, high temperature melt that forms in the mantle. You have to put a lot of that into the shallow crust and allow it to cool off for several tens of thousands to hundreds of thousands of years and let it form Plutonic-sized bodies of granitic magma, granitic rock, in here, in order to keep this part here viable and eruptible, okay, and create several hundred cubic kilometers of erupted magma. So the total size of these systems is, what did I say here? Several tens to hundreds of thousands of cubic kilometer of magma may have been injected into the crust and frozen in here to give us the possibility to erupt one of these supervolcanic size events. This is the kind of picture that we come up with doing this forensic work. So what I want to turn to now is an investigation of an active system. And this is a problem. How do we know a system is active enough to be of interest and has the potential to be a supervolcanic eruption? Well, we have some new tools at our disposal as earth scientists. We're beyond the days of a rock hammer and a hand lens. We bring all the high technology we can to bear on these kind of problems. And principally in the last decade, we've seen this advent of satellite geodesy. And you all have probably grown up. How many of you weren't alive when you heard about GPS? you all take it for granted. You can go anywhere on the planet. You've got, in your phone, you've got a magnificent instrument called a Global Positioning Satellite Receiver. Okay, when I was an undergrad, we had to use a compass and a tape measure and get lost often. Another technique that's used to measure the surface of the Earth and how it deforms is called INSAR geodesy. I'll get into that in a minute. So these tools allow us to look at very small changes of the shape of the surface of the Earth. And they've allowed us to detect where we might expect volcanoes are doing things that you can't see. It doesn't look like much is happening to your naked eye, but we can see that big things are happening underneath the surface. So I'll give you what I think is the best example of that on Earth today in the next few minutes here. There are new kinds of geophysical studies we can bring to bear on these systems, electrical conductivity. We can look at time-integrated seismic behavior. If we have enough money to put enough instruments out in the field, we can actually accumulate long-term records of the seismic behavior. And if magma's moving through the crust, it leaves a seismic signature. It creates earthquakes. Okay, you can't move fluid through the crust without creating earthquakes. And by measuring where those earthquakes occur and how dense they occur in space and time, we can actually look and see where magma's moving and how it's moving through the crust. That's something we can do, and that's only possible in the last few years with numerical and computational approaches to looking at large amounts of seismic data. We can do gravity studies and so forth. Geological, geochemical, and what I like to talk about here, geochronological ground truth becomes ever more important. And we have better and better tools, including the resolution of our ability to date the evolution of these systems, that we can link these basic observations into this data and get a very informed model of what one of these active systems is doing. And then finally, we'd like to apply whatever the latest technology is in computational simulation. I'll talk briefly about that at the end of the talk. So I'm going to take you to a place in the Andes that is a classic subduction zone volcanic system. And I know you're not all earth scientists, but hopefully somewhere in your high school science curriculum you've seen a cartoon that looked roughly like this one, where we have the East Pacific Rise spreading center, away from which grows oceanic crust and lithosphere, and it spreads away from this mid-ocean ridge system, all right, which is the largest mountain range on Earth. This is like the seams of a baseball that envelop the entire planet. On the other side of this spreading ridge, we've got the Nazca Plate, which is growing away from this spreading ridge and moving towards the western side of South America. This would be the equivalent of the Aizu, Bonin, Marianas, and Japan subduction zones over here. This is basically modeled to be southern part of South America. Okay, as this plate spreads away from the mid-ocean ridge and it gets older and colder, it starts to become gravitationally unstable. It's cold, it's getting more and more dense as it moves away from its hot origin over here, and eventually it becomes unstable enough so it starts to sink back down into the mantle. And those of you who followed your curriculum in science carefully realize that this is the engine that drives plate tectonics. The sinking of these plates into the mantle drives convection that helps create the spreading here on in the middle of the oceans. The descent of this oceanic crust beneath the edge of the continent does a lot of things, one of which is critical to getting volcanoes growing on this continental margin, and that is it brings a lot of water in the form of minerals, alteration minerals like clays and micas that form as this ocean floor is moving underneath cold seawater for several millions of years down into this trench and ultimately back into the mantle. These minerals that have water in them are not stable at the kind of pressures and temperatures that they start seeing at these depths, and they release the water to the mantle, which then melts. If you add water to mantle rocks at these pressures, the mantle will melt into basalt. Okay? So we can expect to find volcanoes above that melting zone beneath the western edge of South America. And indeed, there are several hundred active volcanoes along the western side of South America. I'm going to show you what's currently my favorite one of these. I've worked on a lot of them, but I'm going to show you my favorite one right here. It's called Laguna del Maule. It's not really one volcano. It's a volcanic field. So my colleague Wes Hildreth, who originally mapped it, calls a volcanic field. It's located here on this part of the Andes in central Chile. Okay, so it's related to the subduction of the Nazca Plate, as are many of these other volcanoes along the western side of South America. This is a very, very, very active subduction zone. It's one of the most dangerous subduction zones on the planet. If you wanted to pick two places to look at subduction zone processes that are highly destructive and have created many disasters for human civilization, it would be the one in Japan, where the Tohoku earthquake took place a couple of years ago, and this one. Before the Tohoku earthquake took place, this was a spectacular event. Now this is not on people's radar screens anymore, but this is the 6th largest instrumented earthquake that ever occurred. The largest earthquake that ever occurred that was instrumented with seismometers occurred down here in southern Chile along this same subduction zone 2 weeks before I was born in 1960. It raised the shoreline for hundreds of kilometers along the coast of Chile. And Chile was not as populated as it was back then as it is now. The epicenter of this magnitude 8.8 earthquake, called the Maule earthquake, was right here. The Laguna del Maule volcanic field that I'm going to talk about next is right here. It's just inboard, a couple hundred kilometers on the top of the range crest of the Andes right here. And this is just some of what happened during that earthquake in 2010. The volcanic field sits right here. It straddles the Argentine-Chilean border. It's a very large area, several hundred square kilometers covered with young, fairly recent volcanic products. What draws our attention to here are a couple of things. First is there's an unusual concentration of this high silica rhyolitic magma that I talked about earlier, the kind that's the most explosive. In fact, it's the largest concentration of young rhyolite anywhere on the surface of Earth since the last glaciers melted off the Andes about 20,000 years ago, by far. Okay, these are very, very young, all erupted in the last 20,000 years. And then we have the information that the geodesists have shared with us about the deformation that's going on in this region of the Earth's crust. Okay, so we'll look at that. It was revealed to me by a group at Cornell in 2009, right before they published a paper on this topic, that I might want to start taking a look at some of their geodesy results, because they knew that I had been working with Wes Hildreth on this volcanic field for the previous 15 years. There are no historic eruptions anywhere in this volcanic field. It's not an active volcano. It does not show up in the Smithsonian catalog of active volcanoes. There's no historical eruptions here. But what I'm going to show you should get your attention nonetheless. Okay. So our objectives in this project that I'm still trying to get sufficient support to do justice to what's happening here. Our objectives are to look at building a new understanding of the processes that drive these large silicic systems from relatively quiet, unsuspecting states of near equilibrium behavior to those of accelerating unrest and potentially towards large silicic eruption. That's what we're about. We think we've caught one of these systems in the act, so to speak, and we want to do everything we can to try to understand the dynamics of what's going on now before the super-eruption takes place. Okay, so this is a geologic map. Am I standing in your way? You all see this? This is a geologic map due to the work of a very very eminent volcanologist in the U.S. Geological Survey named Wes Hildreth. He's been my mentor on this project for many years. A very senior guy. He spent all of 12 years in a row of all of his summer vacation time that he accumulates from the USGS, taking his vacation time down here and walking around this landscape and mapping it. That's what he does. He's done it at Katmai National Park, at Mount Baker, at Mount Rainier, and so forth, and he's worked on several Chilean systems. This is Laguna del Mali. It's the headwaters to the Rio Mali, which is one of the largest rivers that drain out of the Andes at these latitudes down to the Pacific Ocean. It's about 50 square kilometer lake. This is a very deep lake basin, and all these pink units here are these young rhyolites that Wes has mapped. There are 24 separate volcanoes here that ring the lake basin. Okay, there's about a kilometer of relief, so 3,000 feet. These vents are all up at about 3,000 feet higher elevations than the lake. So this is like a deep bowl here that's completely rimmed by young rhyolite. Okay, all less than 20,000 years old based on the dating that's been done in my geochronology lab, mainly now by my Ph.D. student Nathan Anderson. If you just quickly, roughly sketch in where these young rhyolite lavas are, this is the footprint of those lava flows, and I just do this for you to get the impression across. This is the same exact dimensions of the Long Valley caldera or the caldera at Yellowstone. 25 kilometers by 15 kilometers, something like that. The footprint along which these rhyolites have leaked to the surface in the last 20,000 years is enormous. The scale of this system is gigantic. All right, so about 4 years ago, Matt Pritchard at Cornell called me up on the phone and he said, "What do you know about Laguna del Mali? Because we think it's undergoing some significant changes in the geometry of the surface of the Earth. And have there been any eruptions there? What's going on there?" I said, "Well, mapped it, we've dated it. It's a rhyolite dome field." And he showed us that using this technique called interferometric synthetic aperture radar, he was able to measure some extraordinary uplift in this region, including Laguna del Mali. The way this satellite works is it bounces radar waves off the surface of the Earth, and the travel time and phase relations of these radar waves back to the satellite give you, over large areas of the Earth's surface, several tens of kilometers in diameter, give you a sense of whether or not there's been vertical or lateral changes in the shape of the Earth's surface. And the way the phase shifting works, I'm not going to go into the details, but interferometry is this science of looking at how waves interact with one another. Each one of the fringe bands you see here is equivalent to 112, 118 millimeters of surface change in the landscape, okay? So what this satellite does is it passes over the same region of the Earth a couple of weeks apart, and you measure the phase shift between the two images that the satellite takes over this region, and you combine those, and you can actually see whether or not the surface of the Earth has changed geometry, okay? These are some results that include the early results of Pritchard, but also results of my colleagues Kurt Feigl and his PhD student at Madison, Hélène Lemavelle from France, who's working on her dissertation on this project with us. This is a set of fringe patterns that were collected by using the INSAR satellite between May 5th, 2012 and January 27th of this year. And it doesn't take a rocket scientist to just add up the fringes. I told you each one of these fringes is like 112, 118 millimeters of displacement. And basically this is a giant bullseye that's showing us that the Earth's surface is uplifted dramatically since 2007. We don't have good evidence that the uplift was happening before 2007 when we have the good satellite data, but at 2007 this system really takes off, okay? It's uplifted 1.7 meters, almost as tall as I am, in 6 years. There's no place on Earth that's experiencing this kind of uplift at these rates anywhere, period, okay? This is 28 centimeters a year. The fastest rate that plate tectonics drives spreading from the East Pacific Rise is less than 10 centimeters a year, and that causes all the dynamics of our planet. This is 28 centimeters per year for the last 6 years, okay? If you come back next month, you're going to see a difference in the height of this system. This is data from GPS receivers that were put on the Yellowstone caldera a few years ago, and this is about a decade's worth of measurements of inflation of the surface, this cumulative vertical displacement of the surface at the Yellowstone caldera, this ancient system. Okay? This is Santorini in the Greek islands, in the Greek archipelago, which has also undergone some inflation. This is actually tailed off. This was considered a serious crisis at Yellowstone. This got people really alarmed, okay? Is the world's largest supervolcano at Yellowstone set to erupt again for the first time in 600,000 years, wiping out 2/3 of the US. So this is a crisis that got people's attention. This is what we're seeing at Laguna del Male, where we know there's this concentration of young rhyolites emplaced at the Earth's surface in the last 20,000 years. We have confirmed this with GPS measurements. We have worked closely with the Chilean government, and we've installed 5 GPS sensors on the surface of the Laguna del Male volcanic field, along with some seismometers. You all have grown up learning how this works, but this is a constellation of 24 satellites that orbit the Earth at a high altitude, and each satellite's broadcasting a unique signal down to the surface. And if you have a device like your iPhone now, which is really remarkable, or higher sensitivity instruments set to receive those signals, the satellites can detect very precisely how far away from the receiver they are. In other words, how far away from the Earth's surface they are. And this can give you accuracy at first order with your iPhone to within 20 feet of your location. And now we're using this to drive our cars and not even drive our cars into a building or the oncoming traffic. So this is remarkable. If you process these signals from these satellites and use these spherical geometric techniques to look at the intersections of several of the positions of the satellites, you can actually process this down to get millimeters of change per unit time. And that's remarkable. That's about what we're getting out of the INSAR data. Oops. So these results are obtained by a completely independent method of the INSAR satellite geodesy. And the basic reason to show this is it just confirms what we're finding with the INSAR. We've got 5 of these instruments that are telemetered using solar cells and batteries to get the information beamed down to the Volcano Observatory in Temuco, Chile. And this is actually closest to the center of the basin, and this is the GPS-derived vertical increase in elevation over this period of time, and that's about 240 millimeters per year, 24 centimeters per year minimum at this site. All right, this is very site-specific. This is the uplift at that top of that dome there in which the GPS receiver sits. Very, very remarkable and very consistent with what we're getting out of the INSAR. So we've worked with the Chilean government now. We've got 5 of these GPS receivers arrayed on the top of the volcanic field. Hopefully you can all see that here. We've actually got a few seismometers up here now too. It's very difficult to maintain these instruments here. The mirror image place on Earth for this locality is Lake Tahoe, California. 36 degrees north in California is exactly where this is in the southern hemisphere. This place gets about 25, 30 meters of snow a year, and the winds get ferocious here. And so, in fact, Chilean scientists just went up to the dam here, the outlet dam on the lake last week. The lake is completely frozen over still, but they're having trouble with the telemetry from all these stations. And he's looked with binoculars, all the towers are knocked down. All the solar panels that we put 3 meters high are knocked over now. The winds get to 200 kilometers an hour in here during the winter time. The season that we can work up here is very, very short, okay? Just essentially 3 or 4 months a year, and then the rest of the year is winter. The seismometers have provided some interesting data. I'm not going to go into a lot of detail here, but these are seismic events, earthquakes that have been recorded by this 5-station network that was set up by the Chilean Volcano Observatory that we're working with. This is my colleague Cliff Thurber, a seismologist, talking with Carlos Cardona in Temuco at the observatory. And the main thing here is the earthquakes are all very shallow. 95% of them are less than 7 or 6 kilometers in the crust, so they're very shallow, and they are really concentrated into swarms over time and space underneath some of the more recently erupted rhyolites. And this is a sign that there's magma or fluid actively moving beneath those volcanoes towards the surface. Last year, right when we got into the field in March, there was a big swarm of these earthquakes, and coupled with the inflation that the Chilean government now knows is a serious issue, and they're willing to put more instruments up here with us, OVDAS, the observatory, issued a yellow alert, and it made it into the local newspapers in Santiago. Why is Laguna del Mali rising? Okay, this was in the newspapers literally as we were working on this system last austral summer. I thought I'd just show you a little bit about what it's like to work in this place. It can be kind of fun, but it can be kind of cold and miserable and life-threatening if you're not careful. This is just some shots of us doing the field work. We purchased a Zodiac, which we operate on the lake. In order to get the geophysical equipment around, the gravimeters and seismometers and things, with all the car batteries, we need a boat. So, but it's a very remote place, very dry for most of the year until it starts snowing. For those of you who know him, this is David Tenenbaum, a journalist who accompanied us on the field excursion in March of this year. This is my Ph.D. student, Nathan Anderson. This is Elaine Lemavelle, who's responsible for processing and modeling the satellite geodetic data. So this is kind of gives you a sense of what the landscape's like. And we're going around collecting samples of pumice and ash and lava from these different silicic domes to do geochemical analysis and geochronology. And I can give you a couple minutes of flavor of what that's like. This is the largest of these rhyolite domes at the southern end of the lake. We're taking this from a boat. This is the Baracus Complex. And we've done a lot of work in my geochronology lab dating these lava flows. So this one's 20,000 years old. This one's 6,500 years old. This one's probably less than 3,000 years old, and so forth. Note the elevation here. This is enormous. This is 3,000 feet here from the lake shore to the top of the little dome complex here, but it's not so little. This is looking across the entire basin from just above this vent complex here. This is the Nieblas rhyolite here. This is a full cubic kilometer of rhyolite erupted in one single phase. We think this is younger than we can date it. It's probably less than 2,000 years ago, and that's this big pink mass here. We're looking across the entire lake to the high Andes here on the range crest here. So this is what the landscape looks like. An enormous amount of ash and pumice is in the landscape from each one of these volcanoes. Each one of these pink things is a volcano that did something like what you saw in the video from Montserrat. I'm going to go a little quickly here so I can get you out of here. But one thing we've noticed that Wes drew attention to a long time ago is the composition of these rhyolites is identical on opposite sides of this 20-kilometer diameter lake. And then you have to start thinking about what does this system look like at depth? If the same exact magma is coming out of the surface here and here, are they connected at depth? And that's the question that we want to ask with the NSF's blessing, if were we to get enough money to study this system in detail. My student Nathan's been working on the dynamics of these lavas. These are plots of temperature that we've measured from mineral equilibria and the composition of the magmas over time over the last couple 100,000 years. This is a logarithmic scale. I just want to draw your attention to some of the things we're learning about the system, that this rhyolite, this evolution towards rhyolite is a true flare-up. This is a really unusual thing that wasn't going on in this part of the volcanic system's behavior, but started about 20,000 years ago, and we're pumping out a lot of this highly explosive rhyolite, mainly over the last 20,000 years, down to virtually the present day, but there's been no historically recorded eruptions here. Interestingly, Nathan's found some reversals in the temperature evolution, which signify new magma being injected in here. If this was just one big batch of rhyolite sitting there cooling off, the temperature should be going down with time. That's not what's happening. This gets me nervous because it means that this is being actively filled with magma today. Okay, and that's probably what we're seeing in the INSAR geodesy. This is just some more of what it's like to work down here and putting in one of the GPSs. There's yours truly putting in a 3-4 meter tall solar panel to run a GPS receiver. This is a gravity survey that we did this year. This is a GPS receiver used to precisely locate the gravimeter to look for changes in the density of the crust below this system, which might help us track magma movement. So this is just, again, to give you a feel for what it's like to work in this place. We have some interesting electrical conductivity data. This is work of Martin Unsworth, who's part of our team at the University of Alberta. He has data that was acquired by a geothermal exploration company from these red stations, which are basically a cross-section that includes Laguna del Mali. I don't have time to go into the details here, but the bright electrically conducting region that he discovered here is right below the lake, right where we think the deformation is being driven. And this is always indicative of a large mass of fluid sitting in the crust at these depths. So this is about 5 kilometers below the surface, and that's where we think this magma refilling event is taking place today. So this is really getting to the end of the talk here. We've boiled this down to some hypotheses that we would like to test further, but we think that this system probably looks something like this at depth. This is a cross-section from the southwest to the northeast through the volcanic field at scale. So these are these rhyolitic lavas which have reached the surface. I've mapped some of those earthquakes into the diagram here that we see. And we think there's perhaps a molten reservoir of rhyolite as much as 20-25 kilometers across sitting there, probably being infilled with new magma as we speak. And this influx of new magma is driving this upwarping of the crust on this side of the system. We would like to test this by being able to put an array of seismometers up here and do a much more detailed magnetotelluric survey, but we're still in the throes of trying to arrange support for this research from the National Science Foundation. So this is where we arrive at using all this technology to bear on this system. This is our understanding of the system, and we'd like to go a step further and start modeling it. I've got colleagues at Georgia Tech who are specialists in numerical simulation, and they're working with us to link convection and crystallization in a liquid reservoir that we think is in the crust here, beneath the natural laboratory I've talked about, to link the evolution of this system to the solid crust that's surrounding it and actually see if we can drive the deformation that we're seeing at the Earth's surface. This would be next generation science that we need funding to carry out. We're desperately trying to do this with the NSF. As you know, the NSF is shut down right now, and we're not having great success. So with that, I'll take questions from many of you who have them. Yes?
So one of the classes I'm in right now is dealing with humanities. So I was wondering if you could help me connect how this is going to affect the humanities in general.
I'm not an expert on all the human impacts, but the first order ones that I am aware of are an eruption this size, and we don't know what Laguna del Mali is capable of, but I imagine it wouldn't be on the several thousand cubic kilometer, but given the size of what we see today, hundreds of cubic kilometers is possible. An eruption like that would probably wipe out agriculture in the Pampas, which is the most agriculturally productive part of Argentina. All right, this volcano sits just to the west of the Pampas, and the prevailing winds would blow all the ash downwind into the Pampas. That's a major impact. There are several large rivers that drain this part of the Andes, including the Rio Maule. The Rio Maule has one of the largest hydroelectric systems in the world built up. They've actually diverted the river into big tunnels through the granite, plutons, and put turbines at the end of each tunnel for tens of kilometers. There's like 6 or 7 of these staged tunnels. An eruption the size of what we think could happen here would really wipe out that infrastructure in the canyons leading up to anywhere within sight of this volcanic field, but also the central valley of Chile is the agricultural heart of Chile as well. And these rivers are the lifeblood of the agriculture in central Chile. So the major impacts locally and regionally throughout the central part of southern South America would be those. Globally, I mentioned this earlier, but these kinds of magmas that store the water also can store enormous quantities of sulfur dioxide and fluorine and chlorine. And the sulfate can get into the atmosphere, and it has a long residence time in the atmosphere, and it reflects incoming solar radiation from the top of the atmosphere. So any sulfate that you can put in the atmosphere has the propensity to bounce solar energy out of the atmosphere and cool off the Earth's temperature. Who knows what could happen for a several hundred cubic kilometer ash injection into the atmosphere, but it would cool the climate off perhaps in this part of the southern hemisphere in a band, Coriolis band around this part of the southern hemisphere for years to decades. Would that be good for the climate and good for the crops? Maybe some people would think that's a good thing. We could reverse global warming, but maybe not. Maybe it's not all good. So those are some of the major things that come to my mind.
Just on that last question, we always hear about the theory of the meteor that created such an explosion that made extinct the dinosaurs. Are we talking about similar kind of?
Exactly. I think for a supervolcanic eruption, anything on the order of hundreds of cubic kilometers, 300, 400, 500 cubic kilometers, you're talking about the kind of event that would affect the Earth's surface on the time frame and the scale of the bolide impact that struck the Yucatan Peninsula about 66 million years ago. That was an asteroid, probably maybe about the size of your campus here. And that caused tsunami and tidal waves up into the central part of the United States, into central Texas. And nuclear winter is something people talk about associated with this. Having this much soot and ash in the atmosphere for a long time can block out the sun. I haven't done enough research on this myself because I'm more of a geologist interested in the rocks themselves, but to have this much particulates in the atmosphere for that long certainly would cause some change in the ability to grow crops, I would think, locally or regionally. Some kind of catastrophic climate change might be something we could expect. Could be mass extinction driving, and there's some questions about that. The other way that mass extinctions are generated is by flood basalt volcanism, which is a different style of huge volume magma eruption at the surface of the Earth. That would be massive quantities of basalt coming to the surface of the Earth. Some people think that those drive extinctions, but it's for actually a very complex series of feedbacks, whereas these would probably have much more of a rapid impact on the environment. Those massive flood basalts could inject a huge amount of CO2 into the atmosphere and cause rapid global warming, which could also lead to some organisms not liking it and dying off. It could also lead to acidification of the oceans, warming of the oceans, and destabilization of methane hydrates, which are frozen methane beds around the continental shelves. And if you warm the oceans up enough and you destabilize those, you can actually have a negative feedback mechanism that will exacerbate the climate change by bringing a bunch of more carbon into the atmosphere from unfreezing the methane. Some flood basalts are thought to be linked to those kind of processes. So there are other ways to get volcanism involved here at a human scale to answer your question.
Yeah, I was just wondering, when it comes to environmental issues then, is Laguna del Mar now already becoming contaminated? Because if the magma is flowing in the ground below it, are the chemicals in it, like sulfur, leaching through the soil into the laguna and causing problems for the ecosystem?
This is an excellent question, and we actually don't quite know the answer that you'd think we would. This is a fairly remote area, even for Chile. There's one road that goes across the dam at the north end of the lake. It's a difficult place to access. The Chilean government has just now purchased some ways, tools that they can go in and start measuring the acidity of the lake and for some of these gas species. they're very concerned about the future of what's going on there for exactly those reasons. Are there other signs that we could get for magma leaking into the shallow crust and degassing? One thing we have not found any evidence for fumaroles. There are no geysers, nothing like you see at Yellowstone. It looks dry at the surface. There's no active hydrothermal systems in the shallowest part of the crust. What we did discover in the last 2 field seasons, now that we have our own boat and can navigate around on the lake, there are bubble streams coming up through the lake that at first I thought that's just a bunch of organic matter down there that's been there a couple centuries and it's decaying or something. We brought 2 carbon dioxide probes with us. Glenn Williams-Jones from Simon Fraser University in Canada brought 2 carbon dioxide probes, soil gas probes with us last time, and we actually started measuring carbon dioxide from soil. And we found some whopping signatures on the west side of the lake, 3, 4, 5 weight percent carbon dioxide. And then our instruments broke. They got stuffed up with ash that you can see as a problem in that environment. These were the kind of CO2 meters that people use for incubators in hospitals when premature babies are born. They're meant to make sure the babies don't suffocate on CO2. They're not meant to be taken out here and stuffed into volcanic ash. But we used them as long as we could. Those are whopping signatures of CO2. Rhyolite is maybe going farther than you could. Rhyolite has no capacity to store carbon dioxide. There's nowhere for carbon dioxide to stay in rhyolite. The alarming thing about that then is that it's basalt. It's basaltic magma that's coming into the system to flux it with CO2. So I don't think this cartoon is a too far-fetched. This is mantle-derived basalt, high-temperature magma that's coming into this potentially large body. We don't know how big this is. We'd like to know. We'd like to do a big seismic deployment here to really investigate using tomography whether there really is a molten layer in here this big. But we think that there's good evidence that basalt is intruding this system. And that has that could mean a lot of bad things. That could mean a lot of heat coming in here that wasn't here in the last centuries, and a lot of gas, a lot of CO2, and that could cause convection and growth of volatiles in this part of a magma system. Even if it's only affecting a small part of it, it could help trigger a big eruption. But as far as the chemistry of the lake and killing organisms, there are people fish here all the time. There's no evidence so far that it's got any hazardous chemistry going on or any changes in the chemistry that it would affect the fish population and things like that.
Yeah, I do have a couple of questions. The first is you mentioned the release of enormous amount of volcanic ash. Is there any modeling that would take into account what the effects would be on global photosynthesis? You mentioned briefly that there are some effects on agriculture that would be locally, but if this spreads, you would potentially expect that there be something globally happening. The second part is, would we expect any release of methane or any other highly flammable gases that have an impact on greenhouse effects as well?
So to answer the second question first, I think it's a little simpler. Magmas really don't contain much methane. The big gases that are brought to the surface in magma are carbon dioxide and water, mainly water. Basalt can bring some carbon dioxide. The rhyolites can bring a lot of water and some CO2. Methane is an organic compound that you don't expect to find in silicate melts of the type that I'm talking about, which are common on Earth. So that's not going to be something that the volcanoes contribute to directly. Indirectly, if they do something like if the volcanism has enough of an impact on climate to destabilize clathrite, which is frozen methane, that's another story. The first of your questions, I'm not an expert enough, but I would be surprised if after the Eyjafjallajökull eruption in Iceland a couple of years ago that shut down the airports in Europe for weeks, I would be surprised if after that eruption people aren't doing more sophisticated modeling of how ash moves in the atmosphere and what it does to sunlight and other factors, because that eruption was a wake-up call to a lot of people. That was also a very, very small eruption. Dacite, very similar in composition to what was erupted at Montserrat, actually. For Iceland, unusual, but I don't know specifically to answer your question. Any other questions? There's one in the back here.
Are you able to do any predictability, have any predictability in terms of timing, in terms of chronological? How fast is this moving, this system?
Well, this is an interesting thing that I didn't feel, I didn't have time to go into here for this proof. There are a variety of timescales involved here. If you look at the Bishop Tuff in great detail, this ancient system that erupted 767,000 years ago, we know that from excellent uranium, lead, and potassium argon radioisotopic dating of the crystals that formed prior to the eruption. We know the eruptive age of that system. For the same reasons, we know the sequence of eruptions here over a couple 100,000 years. We know these systems like the Bishop Tuff take hundreds of thousands of years to grow to that size. If you look at the landscape around the Long Valley caldera, you can find rhyolite domes like the ones we see here at Laguna del Mare that were truncated by the eruption. So rhyolitic magma was leaking to the surface for several 100,000 years before the Bishop Tuff erupted. And so that's interesting. We can use those records in the forensic landscapes, or the record that we have here. This is the last 200,000 years. We know something really unusual kicked off about here. Coincidentally, this is when the glaciers melted off the Andes. Maybe magma was prohibited from erupting because of the pile of ice on this latitude of the Andes. And when the glaciers melted off after the end of the last ice age, all of a sudden, boom. It probably took tens of thousands of years to get to a situation where we could produce these rhyolites. This is the big challenge we have, is linking this kind of longer term record to the human scale record of the surface deformation. And that's a modeling challenge, a numerical simulation challenge. In fact, that's where most of our energy is going to be spent on how do we link the best information we can bring to bear on how this liquid reservoir got to a state like this to the solid crust on more human time frames. And that's probably our biggest frontier. So we know it's deforming on this human time scale, but why? What's driving it, and specifically how, and on what time scales are those processes acting? We're not quite there yet. Hopefully, is that enough of an answer?
Yeah,
I don't want to evade the question, but
maybe other people are asking.
I think that kind
When is
of
this going to happen?
this is a huge challenge, and I think it's one of the reasons why we're running up against a wall to get funding. People, what is the value of a study like this if it doesn't erupt in our lifetime? That's the criticism we're getting from the NSF. That's a verbatim quote out of some of the reviews we get. And we're seeing some extraordinary behavior here. This is really 4 or 5 sigma outside the norm for how these systems work. This uplift is phenomenal. The CO2 signal is phenomenal. The magnetotellurics are. It doesn't get any better than this. That's a bullseye for melt in the crust right there. And if you had to make a model to drive the deformation, you'd put a piece of magma, you put a body of magma right here and inflate it, blow it up. Is it going to erupt in our lifetime? I'd say even if it doesn't, we want to study a system that we can catch in this much of the act. That's my take on it. Yeah.
You mentioned on this slide, I don't think I need them, but thank you for the recording. Oh, okay. You mentioned on this slide those red dots. Those were taken by a power company.
Yeah, there's a company. It's a sad story, but they've been bought up by another multinational corporation. They're not pursuing this themselves anymore. But it used to be called Magma Energy. At the time when we got involved with them, it was the biggest geothermal company in the world. They're putting in a power plant. They were. Now it's a Philippine company that bought the concession here. In this valley right here, they're building a geothermal power plant, a 50 megawatt power plant that they can just run a power cord over to the Maule River where that hydroelectric network is. They don't even have to put it in their own infrastructure. They just need to run an extension cord over. That's why it's economic. It's way over here. It's outside of the Laguna del Mare region proper. But there is a geothermal fumarole field over here. And this company has spent several $1 million doing things like magnetotelluric electrical conductivity surveys, or whichever way you want to talk about conductivity, resistivity. They're inverse of one another, as you all know. They did hundreds of magnetotelluric measurements, and they gave us their data. We went and negotiated with them, and before they gave up their rights to the concession here, they gave Martin Unsworth, who's one of the world's experts at using these kind of data to infer crustal processes, the data. We have 3 years of complete freedom to do what we want with it. Now, it's not perfect because they only gave us data from these red receivers and a bunch of data that's up here. This is what we would propose to do if we had all the money in the world. The green dots, that's in our proposals. This is a figure from our NSF proposal. In fact, a lot of these figures are from our NSF proposals. This is what Martin would do if we get all the money we need to do this. And these are big instruments, and they're hard to get in and out of the countries because of the frequencies of energy they require. I'm not an expert on this, but basically you have to set up several sets of these probes wired together over tens of kilometers, and they literally run cable out. It's unbelievable, and they'll wire these things together. And you can measure electrical conductivity gradients between the stations where you put the probe in. So he wants to go with a crew of 6 people for a couple of years and put in stations at all these sites and definitely get around the lake. And ultimately, we want to link these observations with what we can get from seismology. We want to put an array of 40 seismometers up here for 3 years. That way, any earthquakes that get recorded in this region that pass through this part of the crust will illuminate whether or not this is partially molten. But we need a large, 5 seismometers is only scratching the surface. We can see where some of the earthquakes are locally. They're in these regions, underneath the vents for some of these rhyolites. We'd like to be able to use all earthquake energy that passes through this part of the crust to see what the shape and size of this body is. That's a multi-million-dollar effort right there. That's half of the grant that we're trying to get, is to just put out the seismometers for 4 years.
Well, my question actually was going to be, what do you think the impact of those kind of activities, hydrothermal usage in these areas, what would that have on the evolution of these volcanoes?
That hydrothermal reservoir, the geothermal reservoir that they're going after is spatially and disconnected from this system. It's about 10, 15 kilometers to the northwest. And I don't think that's connected by any kind of fracture, fault, or physical pathway. I don't think there's any evidence for this. I'm not sure. Like I said, there's no fumaroles. It's kind of odd. We've looked for them. There's no fumaroles. There are faults. It's not on this. Well, it is on this cartoon. These arrows are real here for a reason. I didn't show you any photographs. So we started mapping in sediments that are being uplifted out of the lake, where this deformation is the greatest, where it's been at 29, 30 centimeters a year. It's pushing lacustrine sediments, diatomaceous sediments, out of the lake. Those sediments are faulting. We can actually go back year after year and we're measuring the displacement on the fault. This part of the crust is extending. That makes me more nervous than some geothermal system popping up. The extension is what could ultimately open this up and decompress it to drive an eruption. Those faults are kind of hard to work with because we go down there with some shovels and things and dig them out one year, and then we go back the next year and it's snowed 3, 4, 5 meters, 10 meters, and you can't find the same outcomes again. But we do want to work on the geotectonics and look at the faulting. Yeah.
You mentioned CO2 bubbling up out of the lake. Is there a potential for a Lake Nyos-like event to occur in this lake?
That's an excellent question too, and I don't know the answer to that. This lake does, get pretty cold and probably have a pretty good, thermal gradient through it. It could trap some of the CO2. Some of us wonder about that. I was blowing off the CO2. We didn't know if there's CO2, and I don't know if all of it's CO2. It looks so ephemeral. But yes, not only we measured it's a very rough measurement with those CO2 meters we have. We need to go back next offshore summer and do a better job with those things. The concentrations are off the chart in several ways where we did make the measurements, mostly on this side of the basin where we know this deformation and faulting's occurring. The other thing we did is we measured the isotopic composition of the carbon, and it's magmatic. It's not organic. It's got a delta C13 value such that it's clearly not organic. So it's coming from depth somewhere like this. How much of it is coming up elsewhere? There's no evidence for volcanic vents in the lake, but the lake hasn't been fully explored for that. It's a pretty remote place. There's really no evidence for any major volcanic features in here. But there could be CO2 leaking out. And maybe this is the only place we're getting the salt. Maybe elsewhere. I don't know. canals, the lake here, this lake is not very deep. Maybe that will help answer, because this lake is only about 50 meters deep at the deepest, 50 or 60 meters deep. This is really to scale, or maybe this is that's exaggerated there, but the lake is pretty thick. Sure.
Why don't we ask one more question and we'll let.
This is par for, in my university, this is par for the course.
Okay, you mentioned earlier about how, the glaciers melted and we saw a change. Would the, isostasy that occurs from the glacier melting and the springing back of the crust, would that affect, the rate at which this super volcano would, happen, I guess?
That's an interesting point, interesting question, interesting point. I don't think the isostatic rebound due to the ice coming off is probably enough pressure change to promote local decompression in systems like this that might help magma gain a little bit of buoyant edge and rise. It's probably not going to affect the long-term evolution of this system. I kind of doubt there's enough pressure in that ice cap. What's perhaps a little more interesting, or something we have had to worry about, is this whole piece of the Andean plate, Andean lithosphere, is moving in a way that it wasn't before that magnitude 8.8 earthquake. There's an enormous elastic rebound effect. Those plates are still moving apart, even though the main earthquake rupture lasted only a couple minutes and affected several hundred kilometers of the Chilean coast, several thousand, tens of thousands of square kilometers of surface area between the two plates. The continent of South America is still moving westward at a vector and velocity that it wasn't before the earthquake. And we have to subtract all that motion out before I'm talking about it's going up this fast, and it's actually, we know it's spreading. I didn't show you the GPS data, but we actually know that this is spreading. We have to subtract out all that other motion that's due to the relaxation of South America over the Nazca Plate. And I'm not the expert on that. It's the Chuck Demetz who's really the brilliant guy there. He knows how to do that. That's something that the Chileans don't know how to do, and they're running around. They've got 43 volcanoes now. It's the largest volcano observatory on Earth. I can tell you the story at lunch. I'll tell you over a beer at lunch so that you can relay it to your colleagues here. But it's an interesting story how they've come into existence, the observatory. Now it's the largest volcano. In the last 5 years, it's become the largest volcano observatory on Earth. They have seismic and GPS instruments on 43 active volcanoes in southern Chile alone. And they're trying to monitor all these systems. This is just one of the 43. We put it on their radar screen, so they put extra resources up here, 5 seismometers and 5 GPS receivers kind of over the top for this group. For the GPS receivers, they're having the woman who runs the network is, all she can do with the software and technology that they have at their disposal, she's looking at the movement of the GPS receivers relative to one another. They don't have the computational horsepower and infrastructure yet to link it to a global fixed network, which is exactly what my colleague Chuck Demetz does. He did one of his postdocs was at JPL, and he invented GPS for plate tectonic. That was part of his dissertation. One of his papers has 6,000 ISI citations. It's called Current Plate Motions. It was written in 1991. He invented the computer technology that allows you to reference GPS motions all to one station that you keep going back to as a reference. They don't have that technology in Chile. We want to get the Chileans up to Madison. That's some of what we're budgeting for in this proposal. We want to bring scientists from Chile up so they can learn how to do this better and monitor these systems better. You'd be surprised we get flack from the Chilean government about this. Oh, these people aren't really scientists, they're technicians. We don't want you taking them from our labs because then they aren't doing their job down here. There's a chicken and egg here, you know. You want them trained so they can really understand what some of the signals they're measuring mean. They could do a better job, you know. But the government, their National Geologic Service is like, these aren't scientists, these are just technicians. We're trying to take a different answer. Like, well, I think you want these people better trained, you know. If you're investing tens of millions of dollars in all this instrumentation, you want the best people that have the most knowledge about how to work with the data on this problem. So it's been more challenging than I thought it would be. Small
remnants that are here. Why don't we take Brad first?